Hello guys, in this short session, let's talk about something called as Blech length. So Blech length is something which is relating to electron migration or electromigration, right? So basically what is EM? Say there is a piece of metal in a due course of time because of continuous flow of current, okay, the metal tends to break, tends to fuse. Okay, there is a displacement of metal atoms which will cause the metal to break and fuse because the electrons tend to migrate from that particular location. Okay? Hence the term electromigration. Okay, so now we have come across in multiple scenarios while doing layouts that we have to deal with IR and EM issues. We ensure we take certain precautions. Okay, so in relation to that, let's look into the other slide. Say, for example, you've got two pieces of metal. One is slightly thinner and one is slightly wider. Say which one has better current carrying capacity? Definitely the answer would be the lower metal, the second one. Why? Because this is wider and the flow of electrons is more smoother. Now, keep in mind that EM is a time dependent issue. When I say time dependent, I would say what I mean to say is it happens in due course of time. Okay, it's not something that, because there is a sudden flow of current, the wire would fuse out. No, it's not like that. It happens in due course of time. So then, what exactly is Blech length? Okay. Now, it's the minimum length of the wire. That's the minimum length of the wire below which the, the metal is not affected by EM. Okay. I repeat, minimum length of the wire below which the electron migration does not fail, which means it is all fine. Anything beyond this particular metal, the metal starts to behave in a reverse way. Okay, the EM carrying capacity of that starts to deteriorate. Ideally, if somebody has to calculate the EM, right? So they would calculate in a circuit this particular design carries say 10 milliamperes of current. Okay, and then you would go with the equation, width is equal to current maximum I max divided by current density, that is 10 milliampere divided by current density, whatever technology you're using, that gives you the width of the metal, right? Now, in lower technology nodes, probably if the CAD guys have this utility set up, or generally, if the PDK is all well set, you have this feature in lots of EDA tools as well, like Cadence, Synopsys, and all of it. We get something called as your EM calculator, okay, wherein you just load the technology node and whatever metal stack you are trying to use, and you mention the width, the type of metal what you're trying to use, and the length of the metal and the width of the metal. It will give you how much current it will be able to carry. Okay, and what happens just as an experiment, right? You keep the width constant and slightly increase the length, keep on increasing. At some point of time, okay, the current carrying capacity tends to reduce. Okay, you can try this experiment, while you're working. You can try, if at all you have an EM calculator. Okay, so you can, load this EM calculator, enter the metal, type of the metal, enter the length, enter the width. That will give you what is the resistance of this and what is the current carrying capacity of this metal for this length. So as and when, if you slowly keep increasing the length of the metal, at some it'll the current carrying capacity increases, it shows better and better, but at some point of time it starts to deteriorate. So that indicates the Blech length of your particular metal. Okay, so when you are dealing with high currents, it is very important that you pay attention to this factor as well. Now, say for example, if you've got a device over here, you have calculated there, for example, 5 devices. You have calculated based on current equation. You have calculated this is the width of the metal what I have to use. Okay, now there are 5 devices here. Now, say for example, okay, if you have arranged a row of devices like this, do you think this metal will be able to carry that much of current? you obviously have to share the sources and drains when you're sharing the devices. Do you think this lengthy metal, for this number of devices, the length of the metal and the width of the metal is fine? But what happens to this scenario, right? The calculation goes wrong over here, right? So in scenarios like this, right, wherein you have to ensure that the width of the metal, first of all, whenever you're calculating EM, right, say if at all the width is, say 1 micron is what you have to use based on your calculation, right? The rule of thumb, what we generally tend to follow is we go 20% more than what is required, just as a precautionary measure, right? When you're arranging the bunch of devices over here. So I don't think this length of the metal will be sufficient. Okay. So there is an alternative way of tackling this problem, right? So what you tend to do is you go with something called as short length routing. Okay, when you tend to use metal, say if this is a device what you have to connect, rather than making a continuous connection of alternating source and drain connections like this with a single piece of metal, you change the style of routing what you do. Okay, you convert it into something like this. Eitherwise, if this is source and this is source, this is your drain, this is your drain, this is your source, and drain, source. Just for example, okay, just trying to show you this is how you make a connection. So this particular metals are much wider, okay, and you make a connection something like this. So what are you trying to do is you're breaking this whole lengthy metal into short pieces of metal. We know that short pieces of metal are always better to carry EM, and in fact they're much better. It'll be able to handle a lot more better EM as well, the short piece of metal, than a lengthy metal, right? So you are making a connection in this particular fashion. This is called as short length routing. Generally we come across these styles when we are dealing with high length high current modules. Okay, so now if I have to go and expand this a little more, say this is how I would make a connection for two similar terminals over here, and obviously gate is on the other side. So I'm doing a alternating connection like this. Okay. So now I have pulled out wide metal ones like this and pulled it out to metal 2. Now you might ask, okay, this is open. What you're doing over here is you're creating shorter connections over here and trying to pull the metal to a higher level wherein the Blech length is a lot better. Okay. Shorter length, shorter metal. Yes, you would do the same for all the bunch of metal. Here I have shown one metal. Likewise, you would do for the remaining next set of transistors. Same replication should be done for the next set of metals. But then as and when you pull the metal, now I have moved from metal 1 to metal 2. I would have a similar connection over here. Likewise, I will move to a higher metal, something like this. Right? It could be metal 3 or whatever, higher and higher. So that's how, wherein this metal, obviously the higher the metal, the thicker the metal, the wider the metal, the better the Blech length, or better the current carrying capacity of the higher metal. You're not putting the whole load on a lower metal. Okay, so you're trying to mitigate the Blech length effect by using the concept of short length routing. So that's how you tackle a Blech length. All in all, if you have to see, I mean, we will be making another video specifically on IR and EM related issues and different scenarios in which, how to fix EM issues, what are the different scenarios. But for now, just to add a little more to this session, yes, how to deal with this, you need to use EM related issues. You need to widen the metal, keep the wire length short. Short, I don't mean that very short. It has to be within the Blech length. Okay, you can use multiple such staples, but short doesn't mean very, very short, but use it something lesser than Blech length so that you don't get into EM related issues. You will feel that yes, I have fixed this, I have used the correct calculation looking at this picture, but ideally you would have gone into these kind of issues. So you have to put small staples. Okay, and then reduce the frequency of the design. Now this is something which we generally wouldn't advise. This, you're trying to compromise with the design itself. The lesser the frequency, lesser the switching, lesser the current absorption, lesser the flow of electrons. I mean, we don't want to go in that direction wherein we are trying to damage the design performance. Even this, lower the supply voltage. All in all, using redundant metals, using wider metals, short metals will help you fix the Blech length issues and of course the EM related issues. So that's about your Blech length. Thank you.